Okay, yeah, I would like to thank you, Vidam. Thank you to the organizers for inviting me to speak and for organizing this beautiful week and this beautiful 6 weeks of workshop. So I'm going to talk about this work on hypergeometric integrals on a punctured Riemann surface. And yeah, hopefully all of these words don't sound scary at the end of the talk. So this is based on the paper we had in September with Andrzej Pokraka and andLecheng, who are all here. Perfect. Yes. But also, if Riemann surfaces of genus 2 and above seem a bit scary, all of this also has a version of genus 1 that we're the three of us, and also Rishab Bardwash, who is now at the Los Alamos National Laboratory, working on quantum machine learning, among other things. So yes, let's see. I think the best way to start is with an example, just to have something very concrete in mind. And the best example is by Euler. Consider the Euler beta function. This is going to be an integral. Looks like this. The S, T, dz over z times 1 z. And for convergence reasons, let's make S and T real. Both of them positive. It's a nice function, and this will be our prototypical example of a hypergeometric integral. It also has a close cosine. So this is Euler 1900s. There is a close cosine. I'm gonna later give some references to why this is an interesting cosine. This is the complex beta function. Now integrate over all of C. Similar conditions, S integrated to 0, and then S plus C less than 1. For convergence. But yeah, so these two functions, very nice, fun to look at, and there is a nice quadratic relation relating them. There's a quadratic relation. I will sometimes also refer to this as double copy. Which relates the complex one to a product of the other one. Geometric function. I'm gonna be a bit silly and put a complex conjugate there, even if it's a real quantity. So now this quadratic relation was actually found. I'm not sure if it was known to Euler, but it was found nearly simultaneously by physicists and mathematicians. In CFT, in string theory, and in hypergeometric functions theory. Okay. So where is the physics? So what is the physics in all of this? Certain question. This is no, I was saying that this is there was known by Euler, but this expression here is actually proportional to the 3-level amplitude of 4 open strings. So the physics, this now comes Veneziano. So actually these S and T's are now actually going to be dimensionless Mandelstam variables for the physicists. Meaning that when I write Sij, I mean alpha prime times Ki dot Kj with massless momenta. And alpha prime is going to be the something that goes like the square root of the string length. Length of a fundamental string in string theory. Similarly, this turns out to be proportional to an amplitude of 4 closed strings. 11. Now this is going to be by Virasol and Shapiro. But I think that really isn't this really cool, because so this is how Kavai level and Tai arrived to this, because they were playing around with this Virasol-Shapiro amplitude and then discovering that you can write it as a bilinear combination of open string amplitudes. Right. What is the physics? All right, sorry. S12 is S, and then S23 is 2. Okay, let me be slightly less. 1, okay. And okay, so physicists know this relation more as KLT relations for Kavai level and Tai. And there's a higher end version of this, meaning amplitudes 3 level, all of it is at 3 level. Amplitudes of n closed strings can be written as bilinear combination of amplitudes n open strings. That turns out to be true. And this is the starting point of our motivation. So I say the word 3 level. Now a bit of like physics recap and motivation. So G loop amplitudes of n strings and as integrals over n0 over mgn call this the moduli space of genus G, Riemann surfaces with n mark points. Being a bit cartoonish, a G loop n, say, closed string amplitudes, then it's going to be an integral over mgn. We will put some measure here, and we will put some function that depends on what n strings you have. And we put these string positions as operators, insertions, and endpoints, and then we integrate. Easier said than done. And then what else is the motivation? And then the other motivation is something very innocent. String theory is no physicists love. For massless states, for massless external states, the upper point to zero limit. So what happens if we take the fundamental strings and make it into a point? Of closed string amplitudes effectively open string amplitudes become amplitudes of gravitons and gluons, but like in just some field theory, that's just particle physics. And this is kind of cool because it also tells you that this on relation, LT relations, if they behave nicely under this limit, then actually this tells you something about amplitudes of gravitons and amplitudes of gluons at 3 level, right? It turns out that this is I don't know how to. Should I use the blackboard like this? Actually, now let's talk about quantum field theory. In perturbative quantum field theory, it's been a nice success story about saying that schematically GR, so general relativity, equals Yang-Mills squared, meaning that there are double copy relations for graviton and gluon amplitudes. And this is the very, very cool part about the field theory part. At 3 level and loop level. And here we can cite, especially for the doing this in the same footing and the same language, Bernd, Carrasco, and Johansson. Henrik Johansson is here. And if you want to learn more, there's a very nice review that I can point at here. That has Bernd, Carrasco, Johansson, and also Chiadaroli and Riemann. It's a very nice, cool thing that, well, in the alpha prime to 0 limit, we seem to also see this kind of double copy structures, these bilinear combinations. So then, is there something like, no, loop level version of these KLT relations. Right? And only recently, we have a nice proposal of one loop versions of KLT relations, meaning for string theory amplitudes. And here the papers to look for are papers by Stefan Stieriger, single author papers, and a paper by Maslumi and Stieriger. Okay, so that's one thing. Seems to be hope. And then one more thing just from taste. So once you have a quadratic relation like this one, there's many ways of proving. If you have true statement, there's many ways to prove a true statement. So what is my favorite way of proving these relations? Is following Omoto, actually, or an descendants of Omoto. There is a very elegant way, of proving this double copy relation, this KLT relations. Yes, I'm still a physicist, still calling KLT relations. Is the theory of hypergeometric functions, which means in practice twisted cohomology. Twisted cohomology. For experts, that means ordinary twisted cohomology. And in this setup, it's a matter of linear algebra. Just linear algebra. There's going to be some vector spaces of integrals and vector spaces of integration contours, and there's going to be non-degenerate bilinear pairings among them. So do linear algebra, and you get these quadratic relations. That's the spoiler for the talk. It's all linear algebra, and we all love linear algebra. Linear algebra how? I highly recommend looking at, there's a 2007 paper by Misera. I think it's called Combinatorics and Topology of Cavalli-Valentine Relations. If you want to see how the linear algebra is done. Okay, so this brings the big questions now. So for three-level amplitudes, KLT relations, three-level amplitudes where integrals over M0n So what do we even mean by asking like what is the loop level version of this? Maybe we are asking integrals over MGN to have like such double copy structures. Now here comes like a bit of the communication barrier between physics and math. Like we see this for M0n being super nice, and we are able to like dream what could be. So we don't know, but I think this is a bit. So this seems a bit more scary to me. So I actually have more expectations in the near future to understand integrals over configuration spaces of endpoints on a Riemann surface of genus G. Compact Riemann surface of genus G. So I have a bit more hope in that, even that seems a bit out of reach right now. Okay. So what we're gonna do is going to be way simpler now. Instead of so integrals over this configuration space means integrating over n mark points. So in this talk we're just going to talk about integrating one function. It's going to be Z1 inside some sigma G, and there's going to be some points removed. Yeah. And also, these integrals will everything that you know and love of twisted cohomology will work. And then there will be a double copy formula for this. So I think now, excuse me erasing, I should probably not touch my iPad. Now, what do I mean by hypergeometric function? So, for a hypergeometric function, we need, now we know where we'll be integrating. So now, we're gonna need a multivalued function. I'm gonna teach you how to think of multivalued functions. So first, let rho be a representation of the fundamental group of this, then call this sigma G star into U1. Then, definition, a rho multivalued function is a function T takes you punctured Riemann sphere and gives us some number. Z1 get mapped to T of Z1, such that for all alpha in this fundamental group, we can just put this fundamental groupoid. We have that T of alpha acting on Z1, meaning we take Z1 and we analytically continue around the loop alpha. From this, we get rho of alpha, T of Z1. And then what we mean by a hypergeometric integral is going to depend on two things also. Some form and some integration contour. And from phi and gamma, and integrate gamma. 1, phi, and 1. But this is just a one form that is holomorphic on the punctured Riemann sphere. And this is, and then I have to say something about gamma here. The boundary operator of gamma has points that are some of these Z2, Z3, Z, which are the removed points. Kind of integration contour that begins and ends. It's really weird because I remove those points. But like, you can still send them to infinity towards that point. And that's it. So yeah, so this is what I mean by a hypergeometric integral. So this is going to be our main example, and the main example is going to be for genus 0, which means sigma 0 is CP1, and sigma 0 star is CP1 minus 0, 1 infinity, P of Z is Z to the S, Y minus Z to the T. Yeah, and I'm gonna just write the beta function as the example. I have to also tell you what the one for my integrating looks like. And it looks like dz over z times 1 minus z. So note that it does, it has poles at z and z equals 0, z equals 1, but it's a holomorphic on the remove. And then the integration contour, I think I will just draw it. 0, 1, infinity, and it's this contour from 0 to 1. Then what else can I say about this the beta function? So the hypergeometric function I'm constructing this way is going to be the beta function. Moreover, I say that this is going to be multivalued, right? It's multivalued because there is monodromies of taking z around 0, z around 1, z around infinity. So note that the multivaluedness of T of z is perfectly encompassed by knowing rho 0. It's going to be the monodromy around z going around 0, rho 1, and well, this is also rho infinity. That's our main example. You can ask questions also. I will just leave Blackboard there. It can also be C star. What do you want it easier to deal with? I want it to be like I only want to have a line bundle when I look at the representation of phi 1 as a local system. Otherwise, I would say that if you had asked me this in November last year, I would have said I don't know how to do any of this very well. Yes. Yes. That's a very good question. Yes. I did, and there's also a topological reason why this is the case. Yeah, because there's a relation in this fundamental group, so that taking the mononomial around 0 and around 1 should be related to taking the mononomial around infinity. And because we're bumping into U1, all of this cancel in the end. But yeah, so this case is it's very concrete, but we can learn a lot about it. Yeah, so now we need some theory of functions and differential forms, and also need something about information about the fundamental group of a punctured Riemann surface. So now let's talk about the fundamental groupoid of a punctured Riemann surface. It has certain generators. I'm gonna call them M2. It's gonna be M generators, gonna be monodromies. It's gonna be alpha generators. You will see which. Beta generators. This will be all the generators. And I'll draw a picture about them. I'm in the fundamental groupoid. So a picture for the case of two punctures, Z2, Z3, is gonna be what? So we can take monodromies around Z2. Remember that this is 31 moving. So this is going to be M2. This is going to be M3. And then there's going to be, I will call this an A cycle. A cycle, alpha 1, an A cycle, alpha 2. And yeah, it's gonna be also B cycles. I'll probably change the wrong orientation. And these loops generate the fundamental group. And there's an obvious generalization for a genus of doing this kind of loops. Let me just put this a bit on top. So then, so because these are generators, then the data of the representation rho is determined by the generators. Right. Yeah. So not much happening yet. So now let's talk about writing some differentials. So when we say that sigma g, without the punctures, is a Riemann surface, we say that sigma g has g linearly independent holomorphic one forms. And we're gonna normalize them. So we're gonna write omega I for this. And we're gonna normalize them on a symplectic basis of homology. And what that means is that picture there, A cycles and B cycles not intersecting among each other, but the ith A cycle and the ith B cycle intersecting each other. Symplectic homology basis. Meaning what? Meaning that when I take the ith homomorphic differential, integrated around the jth A cycle, I get a canonical delta. And then what happens when I integrate this around the B cycles, then I don't have any more freedom anymore. So I get just a symmetric matrix, sometimes a period matrix. So some properties of this, and its imaginary part is positive definite. Matrix. We will need two more things in the theory of functions on a Riemann surface. One of them just requires us to integrate. I like to call this abelian integrals. They are abelian integrals of the first kind, which are going to be defined as what? Take a point, your favorite point, integrate to Z1, and put here omega I. And last but not least, we will need what is called the prime form on a Riemann surface. So the prime form y, I write it with the. So this thing here is something. It's a very funny but useful gadget in theory of Riemann surfaces. I put this square root of a 1 from there because this transforms as a minus a half 0, minus a half 0 holomorphic differential. And then if you want to see a characterization of the one form, I recommend looking at Fay. He has a whole chapter on prime forms, but like a very nice property of prime forms, like Y prime forms. So is that x comma y equals minus y comma x it's a nice function that locally behaves like x minus y. And it's precisely an ingredient to write an Arakelov-Green's function on a Riemann surface. And we can also write it in terms of Riemann theta functions. If Riemann theta functions, but the punchline is, I'm not going to write that formula. The punchline is that it's unique, and it allows you to do very cool explicit things on a Riemann surface. For example, write meromorphic one forms with simple poles. So what we need this ingredient, and we need this ingredient to write our T of Z1, and that's all I'm going to say about it. If someone has more questions, please ask. Yes, good question. E of x comma y is a prime form. So this is just a component of this. So if I isolate it, it just means that I'm just taking some like local section of something that looks like a tensor product of line bundles over x and y of degree minus 1/2 compared to the canonical bundle. So like a minus like 1 over square root of a canonical bundle in x and y, local behavior. And then I would just write the expression in terms of Riemann theta functions, okay? Just to say that it's something. Just to make it less mysterious, E of x comma y over square root dx square root dy is what? Is peak nu, an odd theta characteristic, and if you want something that has this local behavior, funny smart thing you can do is take an odd theta characteristic and integrate integrate holomorphic differential from x comma y and this interpreted as living in C to the G. But then you chose something, you made a choice. I said it's unique. So you have to actually normalize this by something. And the thing you normalize it here is going to remove the choice of the specific odd theta characteristic. And what are these choices? I think people sometimes call them spinors. So what this choice is well, did I write H? Yes. The square of this is the sum from I equals 1 to G of omega I of x, these are holomorphic differentials, times an I derivative on, again, the same odd theta characteristic, now at 0. So this derivative is non-zero. And then you sum over this, and you define the square of this. And then you take square roots such that this behaves locally like x minus y rather than x minus y times pi I or plus pi I. So it turns out that you can do this. And when you do this, you have to do, you go to a covering of the Riemann surface. You can do this. And this, there's such prime forms exist. And it seems that you're making a choice, but it's okay. So I can, if you like a short uniformization, I can also later give you a formula in terms of short uniformization of prime forms. If you like meromorphic differentials, I can also tell you later some characterization in terms of meromorphic differentials. So introducing one form is a bit, prime forms is a bit scary, but then we have all the ingredients to write our hypergeometric integral. In particular, we need some multi-valued function, and it's going to be the following. It's going to be exponential of 2 pi I, sum over I equals 1 to G, of something that I like to call the dot product of Li dot K1 times this abelian integral that I was introducing before. It's nice exponential. And then some product from J equals 2 to N of some prime forms that have theta 1 and theta j to the power S1j, where so this notation is just, so this is just a variable that depends on I, that is a real number. S1j's are also real numbers and satisfy that the linear combination j equals 2 to n of S1j is 0. This is for topological reasons or for momentum conservation if you're a physicist. And also otherwise this expression actually doesn't make much sense. Turns out that with this condition, the choice of point for the abelian integrals here doesn't matter anymore. And this expression here will actually give you a multi-valued function of Z1 with certain monodromies. So now I wanna stress two things about this expression. So this is going to be the key to writing a hypergeometric function, a hypergeometric integral, right? In fact, writing a hypergeometric integral is now going to be, for example, take a holomorphic differential as your integrand, take a contour gamma, which I will tell you about later, and then you just integrate t of z1 and omega I of z1. So it's going to be the hypergeometric integral. It does require that prime form to be defined. You can ask questions when I raise the blackboard. an important remark. T of that one is a part of the covariance factor. The loop momentum dependent covariance factor in the Carroll splitting formalism. So fun. So it's like somehow given to you by physics, such an expression. And then, yeah, also, what is rho? We can read off rho. From T of Z1. So I was writing A cycles, B cycles, and monodromy is around J. Turns out that rho of AI is going to be e to the 2 pi I Li dot K1 there. Rho of J is going to be, that's going around the puncture J, e to the 2 pi I is 1J. And I'm going to write the next one. And the next one is going to be whatever it is, e to the 2 pi I. I'm just going to call it S1bi, where S1bi is sum over I equals 1 to G. Take the pivoted matrix, take L J dot K1. And then sum from J equals 2 to N S1J, and these are bilinear integrals. J, this is I. Yeah. So it is what it is. It's determined already by this. And what about gamma? Now we draw. Okay. The claim is gonna be, okay, pick some gammas. Right. So there's a possibility, for example, gamma 2, 3. And yeah, there's also possibilities of going around like this. Gamma B1. Maybe going around an A cycle. Gamma A2, right? So there's 3 possibilities. So there's 5 such cycles that start as Z2 in this case. So those are gamma. They start at end on some function. Okay. Now comes the cool math. Actually, whenever we write a such hypergeometric integral, and we're giving a pairing between some homology and cohomology. So there's some our integrand phi always belongs, turns out, its class in the end, to a so-called twisted cohomology, which means it's like taking the wrong cohomology, but now you add d log of t of z1 to one form. It's actually a well-defined one form. And turns out that this is going to be isomorphic to, well, there's going to be integration contours in some homology now, with coefficients in a local system determined by rho. And the pairing is the coefficients of the pairing. There's going to be a non-degenerate bilinear one form, which is going to be, well, integrate. But there's more. there is another pairing. I'm going to write the pairing first, which is going to be take the integral of t of z1. So now this is why we wanted u1 in the representation. Take the absolute value squared, multiply by phi and psi, and this gives a pairing with what? Now there's going to be some homology group related to taking complex conjugation. In which this psi is. Similarly, there's going to be another pairing which basically is what? Now it's going to be a complex conjugate contour. There's going to be a pairing here given by the integral taking gamma b, taking psi, and complex conjugating everything. And yeah, so here is going to be a twisted homology group, some local system given by complex conjugated rho. And so this, that, and this are cool non-degenerate pairings, and when these are the only non-zero ones, there's a very nice way here to give a pairing between this and this, which now is going to be, so all of these are integrals, these are just transcendental numbers. But here, this is going to give you some rational function in whatever this representation, these things in the representation. And this pairing here, so once we have these 4 pairings here, we have vector spaces of integrals and of integrands and contours. All of them are isomorphic to each other because all of them have non-degenerate bilinear pairings. And what the double copy is in this setting, for example, in Siren, is simply saying that, okay, I'm just going to do like a change of vector basis of these pairings and then write the pairing above in terms of information of the pairings below. So it's extremely innocent. Yes. In string theory, the Crow string Covan-Nielsen factor exactly enters like this, like absolute value of the open string Covan-Nielsen factor squared, and then here you will see like the corresponding integrand of open strings, and they have so the level of the integrand. It's very funny, yeah. It's basically the recipe in terms of left movers and right movers. So I would like to say there's a very nice 3-level string theory motivation for these integrals here. Otherwise, it's a bit harder to motivate. Yeah. So I am not sure how Aomoto found it. I remember asking another mathematician that studied this at Genus 1, Yoshiaki Goto. And I asked him, why? What about that integral there? About genus 1. And then his answer was, I haven't thought of it. Because physicists will be interested in it. Mathematicians, in a sense, when you have all of this structure, it's very natural. So it's a bit of like searching for the structure, and the structure is very generous, and it will give you the double copy formula. Yeah. So then, what was our... So in few words, what is the main contribution of our... Yes, so I think I have run out of time, so... Okay. Okay, I can keep going. I don't know. I mean, I will soon conclude. I know. Yeah. Thank you. Yeah. Just wanted I wanted all of this to flow kind of naturally and not be very scary. It can be slightly scary. But I would like to say, what were our contributions in this paper? Like, so in 2016, Watanabe studied the cohomology groups. So what we did, because we wanted to say something here about the downstairs piece, we studied the homology groups. Studied the homology groups, meaning how to span them, how to find a basis, and how to obtain these homology intersection numbers, how to compute these new homology intersection numbers for genus G Riemann surfaces. And again, so the theory is very generous because, like, once you have the twisted the homology intersection numbers, everything just pulls together nicely. So now I'm going to say then, as long as this slightly scary looking S1B, all the S1BJs are real, then double copy. And to write double copy in the first place, you really needed to find the homology intersection numbers. And then at the level of more sociological as physicists point of view, and I think also mathematicians do this secretly, we also had some numerical evaluation, numerical control of these integrals. So then we could really see that left-hand side equals numerically right-hand side when writing this double copy, and then we were very happy in that no factors of 2 were missing, or like we really had control and understanding of all of these moving parts. So now I think in the spirit of the workshop, I want to leave with a challenge to all, and maybe motivating questions. How do we extend this? So we're looking at integrals over one function. How do we extend this over more functions, right? Do you have any good ideas? So that's a possible question, and actually I will answer the question I just posed. In that the higher puncture case, the slightly problematic thing of the higher puncture case is that for rho, that really takes you from the configuration space of endpoints over a Riemann surface, right? If you really want a rho into, say, just a C star or U1, this is not faithful. This is not faithful, meaning that you need a version of twisted homology and twisted cohomology that is non-commutative, that is very happy to deal with like these higher dimensional representations of fundamental groups. This is, I would have had no idea how to do this 4 months ago. I still have no idea how to do this. But there was a very recent paper by Kakat, Ochirov, and Zhang, in which they introduced Kakat, Ochirov, and Zhang, December last year. They introduced precisely a non-commutative twisted cohomology. And why? To give a very nice proof of the KLT relation on ADS amplitude, on the Virasoro-Shapiro amplitude in ADS. So I suspect that this will give help to understand what to do in the configuration space integrals if there is something to do. But yeah, if you have looked at that paper and want to talk about it, I will be happy to also talk about it. I will be happy to tell you much more about this paper also. If you are interested in numerics or like functions and Riemann surfaces, yeah, I'm very happy to talk. But yeah, that's it.